Okay, in the next two videos, we want to talk about first order systems and second order systems. If you have taken vibrations or similar courses before, you have some understanding of first order and second order systems. Here we study the same concept, but a little bit different. It's going to be systematic view rather than being from vibrations point of view. So this video is going to be about first order systems, and then in other videos we would discuss second order systems. So first we start with the definition of first order systems, then we study step response of a first order system, and then we study graphical method to estimate gain and time constant of a first order system. So to see where we are, so initially we have studied how to model a system, different ways to model a system, from ordinary differential equations to transfer functions, block diagrams, and state space representations. Then, having these models, we want to learn about system or behavior of the system. So now we are discussing those things. We are studying behavior of a system, and we are focusing on the behavior of our systems, which can be first order or second order. Okay. So what are some applications of first order systems? They are in a lot of applications around us. RC circuits are first order systems. DC motors, DC servo motors are first order systems. Their differential equation looks like this, equation number 1. So this is a first order differential equation. What does that mean? It means that the variable of the differential equation, here y, appears. In addition, the first derivative of it appears too. That's why it's called first order system, because the variable of the differential equation and its first derivative both appear. But we also have another variable here, the input, or u. So we have an output, or y, we have an input, or u, and the output's derivative appears in the differential equation. There are a bunch of other parameters here too, like tau p, kp, and then theta p, which are just the parameters of this equation. So when you see a first order system, these are just going to be numbers. So what is tau, what is k, and what is theta? Theta is the delay. For the rest of this course, we assume there is no delay. What does delay mean? Meaning that if I give an input, the output appears with some delay. Imagine you give some voltage, you apply some voltage to your DC motor, and it doesn't instantaneously, it doesn't start moving at that exact moment. Let's say it waits 1 second, and then it shows the result of the voltage you applied to it. That delay is going to appear here. For the rest of this course, we assume that that is not the case. There is no delay. So equation 1 simplifies to this equation. It's just the same equation without theta. Now, if I take the Laplace transform of this differential equation, I'm going to have this. So the equations that are important, we put in this presentation and other presentations after this, we are going to put them in a box. So the box is going to show that you need to probably memorize them. So for a first order system, its transfer function is going to be equation 2, the ratio of output to input, which is the transfer function's definition, is a fraction with no zeros, right? There's no s in the numerator, and only one pole. What's the pole here? It's -1 divided by tau p. So the first order system's transfer function has one pole. But we see here two things. We see kp and tau p, which these are gonna be numbers. These are parameters of my first order system. What are tau and k? Tau is the time constant. What's the definition? Well, time constant for first order system is the time required for the output to get to 63% of its final value. So let's read it again. It's the time required for something to happen. So it's a measure for how quickly system responds. That's why it's called time constant. It's a number that shows you how fast the response of this system appears. Okay, so that's time constant. Settling time for a system, for a first order system, is defined as the time for the output to converge within 2% of the final value. So the simple way of saying it is that the time that we are almost sure that we reached the final value, the end of the story for this system. And the rule of thumb is that if you wait 4 times time constant, we get to 98% of the final value. So if you want to see the end of the final response of your first order system, wait 4 times that time constant. Okay. Now, having a first order system, what happens if we apply an input to it? Specifically, a step input. Well, let's say we have a step with magnitude of capital A. So it's not a unit step, it's a step with the magnitude of capital A. If we plug in U as A divided by S, the Laplace transform of a step with magnitude of capital A is A divided by S. And we apply partial fraction expansion and take inverse Laplace transform and then take or factorize it, we are going to have equation 3, which is the output. So let's go back. We had this equation, we substituted something for U, and then we are trying to find not y of s, but y of t, so the inverse Laplace transform. This is going to be the time domain response of a first order system. Now, if I actually plot this, how is this going to look like? Like this. So a first order system's response in time to a unit step, to a step is going to look like this. So the final value of a first order system's response to a step with magnitude of capital A is this, is capital A times Kp. So, and that's how it appears here. If t goes to infinity, you're going to have e to the negative infinity, which is 0. So what remains is capital A times Kp. So let me repeat again. If you have a step with magnitude of capital A, your first order system not only would have that capital A, but it actually goes up to capital A times Kp as its final value. That's why that Kp is called gain of the system. Let's go back. Kp appears here in the numerator. We studied that tau p is the time constant, and we realized we call it time constant because it's a measure of how fast the response is. Now we learned that the name of this KP is gain because it's a gain. It multiplies to the response. If that gain is 2, your response to an input with magnitude of capital A would be 2 times A. If you wait long enough, the output would end up being 2 times A. That's why it's gain. If it's half, your output is going to be half of the input if you wait enough. Okay. Notice that we got this result only because the pole of the system, which was -1 divided by tau, is on the left-hand side of the plane, S-plane, meaning that our system is stable. If we had the first-order system, but the pole wasn't negative, if the pole was positive, meaning that your system was unstable, that wouldn't be the case. I would also not get this plot if the pole was on the imaginary axis. We're going to see it in the next few slides. We're going to see what that means. So we are going to see general possible responses based on the location of the pole, and we are going to study them. I also recommend you looking at this animation, the link for first-order systems and how they respond if you change the time constant. It's very interesting, and so I recommend looking at it. But yeah, so we see 3 graphs here. We see unit step response of systems 1 over s, 1 over s minus 0.5, and 1 over s plus 0.5. So 3 systems, they're all first order. The pole of this one is at the origin. The pole of this one is at positive 0.5. The pole of this one is at negative 0.5. Okay, so yellow, which is 1 divided by s plus 0.5, behaves the way we just talked about. But if you have pole on the right hand side, your response goes to infinity. You have an unstable response. So notice that when we talk about the behavior of first order and then later second order systems, we just are talking about a specific family of them, the stable ones. Now let's assume that we have a stable system. We want to see what happens if we change tau and kp. What happens if we have kept the gain constant but changed the time constant. So gain is 3, but I have increased tau from 1 to 12. So gain is 3, but I have increased tau from 1 to 12. Let's see what happens. Well, blue and red have the exact same, they're identical for their final value because gain is the same and the input was the same. It was a unit step. But what is different between these two responses? Well, this one is much faster. This one arrives to the final value almost here. For blue, it takes forever. So blue is much slower. The only thing that is different for them is tau, time constant. Now, if we keep time constant the same, so look at green and yellow, time constant is 12, but gain has changed from 2 to 3. So compare yellow with blue. Their speed is the same because the time constant is the same, but blue ends up somewhere somehow higher because the gain is bigger. Okay, so in the next video we study graphical method to estimate gain and time constant.